Okay, so yeah, so brain-body co-evolution, that's the topic of our koan, and this is going to be the outline of our presentation. So we're going to start with a little why are we actually doing this? So why might it be interesting to do brain-body co-evolution? So motivation for this topic, and then we're going to describe the different softwares that we've considered for this task, and for the idea we had. How to explore brain-body co-evolution. And then we're going to present the software that we eventually ended up with, that is RoboGen. And Julia is going to present this part. And then we're going to start by showing you our results in some videos on the brain evolution part, so evolving only brain and hand designing the robot body in two different scenarios, so in two different and then for both of these environments, the racing environment and the chasing environment, we're going to present the co-evolution of brain and body. So, okay, let's start. The motivation for doing brain-body co-evolution. So why would we actually do this? Why might this be interesting to consider the co-evolution of brain and body? And the first part, obviously, is, well, this is what all the species on this planet are doing, the concurrently evolving brain and body. So it's definitely biologically realistic. But why might this be interesting for the species of this planet and also for robots and artificial agents? And this basically relates to many of the points that were mentioned in the lecture series. The first one being morphological computation. So if the body is involved, there's a chance that the solutions that come up will be able to outsource some of the computation to the morphology and environment, which is known as morphological computation. And then secondly, it's also interesting because the possible bodies that we as humans can design for our robots is kind of limited. So there's always a designer bias in what we can actually design for our robots' bodies, but evolution doesn't have these limits. And then the point of emergence is also very interesting because by doing this co-evolution, we can hope to end up with like emergent solutions for some, I don't know, for some tasks and problems that yeah, we couldn't have predicted entirely from the controller, for example. And then lastly, there's also the argument that there's the interaction between these three parts, that is body, environment, and controller, will be more easily achievable in this co-evolution setting. Yeah, so this was our motivation, and then we started exploring. Okay, how can we actually do something with this? And there we go. And what software can we use for this? And then we started with exploring Ludobots. But it turned out pretty quickly that this software wasn't actually what we were looking for, because it wasn't mature enough actually for what we were planning to do. So there were like some difficulties in customizing, and there was a very limited possibility to actually evolve the body. Yeah, and then we considered robots, but we discarded this idea also very quickly because the morphology of robots in this robots simulator is encoded in XML files, and that would have been extremely painful to modify. So we were hoping for a software that would provide us with basic functionality for body evolution. And this is where we ended up with the software RoboGen, and now Julia is going to tell you all about it.
Okay, so this software is developed by a group of scientists at the EPFL, I think, and it comprises two components, an evolution engine and a simulator. What the evolution engine does is, just like in normal evolution, it will take care of reproducing the individuals and of selecting them. So what that means is that we start with a set amount of individuals, in our case 5. We are going to combine their genomes, and we're going to select the fittest one for the environment given. And the simulator evaluates this fitness of all our robots. So each robot will have a controller, which is the brain, and in our case, it's a fully connected recurrent neural network. The input layer will be comprised of the sensor values and the actuator values at the previous time step. The body is represented by a tree diagram, each body part being designated by a unique letter and number. And the body parts that we use, you can see on this slide. So we have wheels, legs, core module. So the core module is the most interesting part because that's the actual brain of the robot, and it houses a microcontroller. Then we have joints, and this is a light sensor. RoboGen also gave us the possibility to use different types of joints and also touch sensors, but we didn't use them for our project. Okay, so we showed you what the brain and the body are, and now we're going to explain a bit the parameters that we used. So, as I said at the beginning, there were two parts to the program. One was the evolution engine and one was the simulator, each of them coming with their own parameters. And there were a lot of them that we could tweak, but we didn't have the time because it was quite a short project. So we only changed some of them. For example, mu and lambda are the number of parents and offspring. Then the number of generations, well, is the number of generations that we're going to iterate for each evolution run. The evolution mode is very important. It can either be full, meaning that we evolve both the body and the brain, or brain, in which case we only evolve the controller of the robot. The p-brain mutate is the probability of getting brain mutations. What else do we use?
Crossover.
Yes, the crossover as well. So it's also the probability of combining the genomes of two individuals. And then we used some other ones, but they're not important. Okay, and then for the simulator, we have the racing and the chasing scenarios. The difference between them is that racing means that the robot has to cover the longest distance in a given amount of time, and chasing means that it has to approach a source of light. Then you can also change the terrain dimension, the obstacles you have on that terrain, and the starting position of the robot. Also the height of the light source. Okay, so now we're going to show you our results. I was in charge of the brain evolution part, and I came up with different morphologies that were created by hand. And why I did that is because the initial robot provided by RoboGen was not, well, it was very simple and it wasn't doing much. And then I used different starting positions, so our robots wouldn't develop an optimal solution only for a starting one, so we would vary it. And then we also changed the brain mutation rates. And you can see what we got. This is the first robot. It's not doing much. It spins in place. But then I changed the morphology a bit, and what I ended up with is this. So you can see here a very good example of morphological computation. The robot is using its body to propel itself forwards. And so it's just running away. Okay. So this was my part, and now Matthias will show you his results.
No, isn't that your part?
No. Oh yes. Oh yes. Sorry. So I also used the chasing scenario, in which the robot had to approach the source of light. And this is what I came up with. So it's the same morphology of the robot, only a different scenario, and the same terrain, the same obstacles. Okay, and now Matthias will show you the brain-body coevolution. and Enrique will conclude our presentation.
So yeah, so you've seen that in Julia's case, the robot body was hand designed, and she also showed you the solution, what the evolution algorithm came up with for the chasing scenario that is approaching this light source that you see here in the center. And now this robot that I'll show you next, is one of the more successful robots of this scenario. We have to say that as there were so many parameters to tweak for this evolution, we had at the beginning I personally had many problems coming up with an interesting solution for the robots, because most of the time they were just stuck in a local optimum and had like crazily complex bodies that weren't doing much. So this is probably because you have to actually find the right parameters, but we didn't have the time to do like an extensive parameter search on this. However, this robot that I'm going to show you now it's kind of doing what it should do. You're gonna have to wait a little bit because it's a slow one.
Oh,
can you fast forward it? Okay, cool. Okay, now this is in fast forward mode. Yeah, and you can actually see that this robot, it's a very simple robot. So it has just two motors, like a wag and a wheel, and then 2 light sensors. I hope that you can also see these light sensors in front of it. And this is already, I think, like very primitive, not so elegant Breitenberg vehicle here, because it has 2 motors and 2 light sensors, and it's actually able to orient itself towards the light source and then approach it. So it's kind of like a little bit like the loving or maybe the aggression type Breitenberg vehicle here. So this is very interesting, because we at the beginning when we started our project, we were hoping to achieve these Breitenberg vehicle types of robots, because especially for this chasing scenario, this would be a solution that also we as humans could have come up with for chasing this light source, because it's a typical Breitenberg scenario. Okay.
So now we'll show you. As I said, we didn't manage to record the video, so we're just going to show you via the camera on another computer. It's another interesting one that can climb stairs. Okay. Can you see it?
Yes, we can.
Right, yeah, as you can see, this robot again tries to approach the light source. So this is the fitness function again. But this time the terrain is different, because we have these stairs, obviously. But after a few thousand generations, it actually also manages to climb these stairs with a very rather complex architecture, so with a rather complex body. But yeah, it works.
Okay. Enrique, it's your turn.
Okay, thanks. I'm sharing my screen. Okay. So you can see the presentation. Hello.
Yes.
Hi.
Hi.
Yes, I'll put it on full screen now.
Sorry.
One second.
So my part was to perform the coevolution of the brain and the body in the racing scenario. As Matthias said before, I found out that the body evolution just give us some really strange robots. It was quite complicated to get a functional robot to do such a easy task. So when I started, I think about several objectives. I wanted to know how the environment would affect to the evolution. So we can see here, I used 3 different environments. We can see one plane surface.
Enrique, we are at the last slide. I'm not sure if it's just our problem, but we can see your last slide.
No, I don't know. I'm trying to share the binary body convolution, so it seems to not be working.
No, it's working. Okay.
Okay, I cannot. I have the same problem like you. I cannot do full screen, so
Okay.
I'll go. So again, as I was saying, I used three different environments. We can see here the pictures. The first one is a totally plain surface without no obstacles. We can see here another one with just a few ones, but the robot still has a clear path to go away. And the last one is this, where the robot is surrounded by obstacles, so it's harder for it to go a big distance. For each of these scenarios, I change several parameters to see how it affects, and in general, here. The best results I got were for the second case, I mean the low density object environment. I noticed some other things, like the fact that increasing the number of generations, as for any genetic algorithm, it would mean to get better results unless you reach optimal state, so the evolution would not go further no matter how many generations you do. Well, although the best results were for the second case, there was a big number of tests where the first case, I mean the plane surface, showed the best results, but the difference between these and the others were not very significant, so it can be just case of some random parameters of the algorithm. We can see here one of the robots. This one, we can see that it starts slowly. This is a problem because we used the first 8 seconds of the movement to calculate our fitness value, so it can give some strange results, but we can see at the end it moves quite well and starts going away from the screen as in the other cases. And then I came out with this other robot that it looks more complicated and more strange, and although it has 3 wheels, it used no of them to move. That's a bit strange. We can see that as in the earlier example, it takes some time to start moving, but in the end it's able to move itself in a straight line and travel a great distance.
Sorry, Kiki, I can still just see the first slide for brain-body co-evolution racing scenario. Is that correct?
Yes, it's the same problem for us.
Yeah. Could you try to? I can.
Which slide are you seeing right now?
It's called brain-body co-evolution racing scenario, and it's got 3 pictures on it.
It's your first slide.
Number 15.
Why is not changing this? I'll try to change it to share the.
Share the application directly, maybe.
Yeah, no, that's what I was doing.
Okay.
Okay, so it's now changing, or?
Now I can see another one. Yeah.
But I see in your screen that it's not changing. It just stays in the same slide. I'm trying to change and I don't see anything working.
Yeah, I can see slide 16 right now.
I'll try to share the whole screen. So.
Okay.
Oh. No.
Yeah, we can see it there.
Slide 16, and it's changing now, or?
Yeah, it's a bit small, but we can see it.
A little bit bigger.
That's nice. Okay, try that.
Okay, so as I was saying, sorry for all these problems. I run 3 different environments for 3 configuration of obstacles. We have a totally random initial robot morphology, so the evolution engine will create the initial robot and start evolution. And after running different tests for each one of these scenarios, I came up with the conclusion that the best overall result was obtained for the low obstacle density environment, although the plane surface showed the biggest amount of better results. But the difference between those results and the other were not quite significant, so I think the final conclusion would be that the second environment gives us the best results. Apart from that, I've noticed some other things like changing the number of iterations would mean getting better results as for any other genetic algorithm, unless you've already get to an optimal point, so it doesn't matter how many other generations you run if that doesn't evolve more. Here we can see the first robot. As it's a slow starting, but then it starts moving in the right direction. It moves quite well for the results. This was obtained after running, I guess, 10,000 iterations. So it took a very long time to come up with a good solution. And we see it moving and going away from the screen. And I've got another robot here that looks a bit stranger also because it has 3 wheels, but it won't use them for moving. It moves using the web. As the example before, it takes a bit long to start moving, but then it starts in a move in a straight line, and it kind of do its work because the robot is able to travel a big distance. And it ends also leaving the whole environment. So these two were the best robots we achieved in this particular scenario, but almost all the robots were totally stupid and really strange. These two were the only ones that were able to do something competent. So to sum it up, this is our final conclusion. We evolved two types. Well, we performed 2 types of evolution. First, we tried to evolve only the body, only the brain. Sorry, here's a mistake in the slide. And both the body and the brain at the same time. We tried to set the effect that the different parameters have over the evolution, like the scenario, the brain mutation rate, and another parameters. And we see that if you're trying to evolve both the brain and the body, in the grade, many of the robots were really primitive, strange, had a too complex configuration, and couldn't achieve this kind of task in the better way. And it's also very time consuming just to not just exploring all the parameters, but running the number of generations you need in order to get a good solution. So we can see that for this kind of task where you have a really simple goal with a really simple environment, brain and body evolution is not the optimal course of action, because we all know how to build a basic robot that can move just in a straight line. It has no hard requirements for a body complexity. If you start working on a bigger project with a more complex objective, then yeah, the brain and body evolution would show the best results and will save you many time and many tests, many trials of different bodies, because it would adapt the body to the objective of the scenario. Different solutions we came up with. as I said before, try to design complex bodies by hand and evolving the controller, although depending on the complexity of the task, this could be a bit complicated. So we also can try to just to stick to simple bodies and try to evolve the brain to see if we can get some complex behavior that would overcome the limitations of the body of the robot. And by the end, the last one was trying to limit the body parts using for evolving the body to those we know that are useful in that particular scenario. Because right now the evolution engine had access to all the parts in the program with no limitation. I think it can use from 2 to 10 different parts in order to create the robot. And maybe if you try to reduce that number or just use wheels and part of the body, it would be better for us. So this is all. Thank you for listening, and if you have any questions.
All right, thank you very much. Let's give an applause to the group. Thank you for a very nice presentation. I'll now open the mic for comments and questions from the panel. Any questions? Okay, Carlos, yeah.
Hello. Well, first of all, nice presentation. I like your work. I have a couple of questions that I wanted to ask you. Maybe the first one is for Julia.
Yeah.
Because, well, Enrique said that the training or the generative algorithm took like 10,000 iterations for the combination of brain and body. But I was wondering, how did this or the generative algorithm work for just the brain? I mean, how long did it take to train or to get to a proper solution?
It depends. We also tried a lot of generations. So I tried with 10,000 as well. And with 100, I think it didn't depend so much on the number of generations in this case. So if it found an optimal point, sometimes it would find it even after 100 generations.
Yep.
And I think it's easier than to evolve the body and the brain together. So yes, I think we can use a lower number of generations for that.
Okay. And I don't know, the second question, who is directed to, just let me know who you think is better to answer. I saw this kind of monster robot that you came up with in your last approach. Do you think is there a way to limit the number or to select in a better way the amount of wheel sensor, I mean components in general, to came up with the thing is, strange robots are okay, but if strange mean that some parts are not usable or are not going to be used, do you think is there a way to limit this?
Yes, so that's what Matthias did actually. We limited the number of parts, and it's easier. Yes, you can come up with better suited robots.
So you can do two things. You can like limit the number of body parts that the robot can have. Like I did like 20, and then you can also limit the number of different parts, because you have like overall you have like a choice of I don't know how many different parts, like wheels, wax, and different kinds of joints, but you don't need to use all of them. So I also limited this to the most essential ones, like wheels, light hinges, and bricks, just in the hope of coming up with a simple solution.
But the problem is that if we don't add joints, for example, so Matthias tried doing that, the robots can't really do anything, because it's difficult to have the bricks and then the core modules and then the wheels connected directly to them. So it's better to have some joints, but not too many, because then you will have a robot that does very funky things because it has too many joints and its legs are too long.
Okay.
All right, thank you. So you talked about in well, mainly the conclusions that it's maybe for a very simple implementation, to get a real working robot, you might as well put it together yourself. But when you're moving towards more complex designs, that this type of evolution of both brain and body could be useful. Can you think of any type of real-world application of robotics right now where this type of approach would be useful? Is it possible to do something like this for a real robot right now?
For example, sorry.
No, go on.
For example, for disaster areas where you need little robots that have to go between, I don't know, crashed buildings, for example, and where they have to enter very small spaces, or for example, if it's a specific environment, like if you have a robot that has to travel down tubes or sewage pipes, that could be useful, because we don't know how to come up with such a robot ourselves, but
I mean, you need to know a bit of things about your task. If you don't know the environment, you can't come up with a good solution by evolution. So, in tasks where the environment is not known, or it's a dynamic environment with moving obstacles or different conditions, this couldn't be really useful. But for application where you can take the time to train the robot to look for a good solution, then yeah, this could be a possibility. Although right now I can think about a really real application for this, but that's it. I mean, you need some basis, and the more important for me is that you need good task knowledge, because if you don't have, you cannot know if your robot is going to perform well that task. So the evolution doesn't seem to import so much.
Okay. Any other comments or questions?
Yes, I'm not surprised by your results, because actually it seems that your results point to an issue in evolution that some have noticed before. No, the fact that someone says that the time frame that was necessary to achieve the complexity of life that we have on life on the planet now was probably bigger than what you may achieve just by trying random. So I mean, this is controversial, but for instance, people like Stuart Kaufman says that there must be some directional mechanism in place beyond the poor trying and select mechanism of a standard evolutionary algorithm. So, of course, this is controversial and it's not clear how to do it. You may have noticed that in the example on morphology evolution by Josh Bongard, that you can find in the repository of a lectures. He used the genetic regulatory network, which is a more complex mechanism, which allows you for instance, to put constraints on what you can do. No? For instance, if you put wheels, put them 2 by 2, or things like that, because trying at random and having the short time frame that you have, probably what you find is bad, no? Because on one side you find some locomoting robot, which is really different from what you had imagined yourself, no? The one with using the legs to move and using as support, but they are acceptable solutions. I don't know, did you think, the lateral comment is that I think you may have used both Ludobot and Webots. Vaughn Webots, you should have developed an interface to edit the XML file, which takes more time than you had. So thank you for suggesting RoboJam. Probably we will use in the next editions. We will also make available it. So this is a very good contribution. But I would not be so sharp saying that you should evolve the body and the brain separately, because more or less you say, okay, I design the body and then I evolve the controller. I don't know if you checked with what you had so just to make a question. If you checked with what you have available, if you could put some constraint not only on the number of elements and number of kind of elements, but also on the ways you can connect the elements in RoboGen, if you could do something like that. So to constrain the fact, for instance, having only pair of wheels, not the 3 wheels or 5 wheels.
I don't think that's possible directly. So I'm not sure, but implicitly this is already kind of present in one sense, because there's a parameter like, so the robot body is encoded in this tree structure, and the mutations on this tree, like there's you can remove or add nodes in this tree, but there's also a mutation that just duplicates one of these trees, or deletes one of those trees. So if you would like restrict the mutations to these types of mutations, so not inserting nodes all the time, but only copying, I don't know, tree structures that you already have, and this might also, yeah, put constraints implicitly on the connectivity of the different parts. So maybe, yeah, one could explore that.
I see, because as a final comment, I would say that apart from suggesting this tool for the exercise, RoboGen, I think that your work actually highlights some really slippery issue in the model, in the theory of evolution. So in fact, it's not so clear how you should direct, because you know that there was this very old issue between the Lamarckian view and the Darwinian view. No, but Lamarck says that it's adaptation. The adaptation of the agent is transmitted, while actually the standard and received idea about evolution is that you try at random and you select, and the good solution reproduce faster. And then you have epigenetic, which means that the way that the genome is expressed depends on the environment. And then you have this minority point of view, like that of Kaufman, which says that, well, maybe there is some kind of direction. So it's very nice. Thank you for nice work.
Thank you. So final comment would be that RoboGen is very good compared to the others because it has an extensive documentation. So it's very easy to implement.
Okay. I think we will add it in the list of available softwares in next edition. Thank you.
I want to do some comments about the RoboGen 2. One really cool thing is that the program actually allows you to build the robot you have created. The robots are designed with really simple pieces and using really simple electronics, so you can actually print the body of the robot using a 3D printer. That's a really cool application, and you can using just basic electronics like Arduino and sensors that you can buy anywhere. You can see how after you have simulated, run the test, and get the robot evolved, you can build the actual robot and see it moving in the real world, so that's kind of cool. And also say that this is a research project, it's not a closed software, it's not a commercial version, so if you want to change it, I mean, it would be complicated, you need to take some time, but you can adapt it to your needs. So I think are two characteristics that are really nice for this program.
Okay, thank you for that comment, and let's thank the group again. Thank you very much.
Thank you.